All right, so let's take a look at an example where we're integrating over a three-dimensional region with variable density. So here our region is going to be bounded by x squared plus y squared equals 1. So that's the cylinder r equals 1. And it exists between the horizontal planes at z equals 4 and whatever this surface is right here, z equals 1 minus x squared minus y squared. Density is going to be proportional to the distance from the z-axis, which is r. And we want to find the mass of this object. Okay, so some observations, let's see. So this one right here, this is r equals 1, right? So that means, that means that we are looking at a cylinder, something that looks like this, maybe take it down a little bit more. Okay, so there's our cylinder. And we've got the plane z equals 4 right here, so that's a horizontal plane. And then we've got this one, which is z equals 1 minus r squared, right? If you just parenthesize it a little bit like that, you see it's r squared. So that's going to be a parabola opening downwards, paraboloid opening downwards. And so it's going to, let's see, so for 1, bam, something that looks like this. And so let's see, so if this plane here is where z is equal to 0, we can see that this is the unit circle in the z equals 0 plane by just actually substituting this expression here in right over here. So when you do that, you get z equals 1 minus, and then we substitute x squared plus y squared equals 1, we get 0, so that's the z equals 0 plane. So this horizontal surface right here, this is r equals 1 like we saw in a previous video. And then this paraboloid down here, this is the z equals 1 minus r squared. All right, so what does it look like? It looks like basically the bottom part of a wine bottle, right? So it's a cylinder, but then somebody's like cut out this sort of paraboloidal shape out of the bottom of the wine bottle. All right, so I guess the last missing piece is this density is proportional to distance from z-axis. So the distance from the z-axis is r in cylindrical coordinates. So that's telling us that our density looks like r times some constant of proportionality. Okay, that'll be our integrand. And now we just need to figure out how to set up the integral for this. So when I look at it, one of the first things I see is we have z equals this and z equals that, which is kind of a nice suggestion that maybe we want to first do a vertical integral in the dz direction. So if we do that, let's see, we're going to be starting then at this bottom surface down here given by the paraboloid. That was a bit messy. And then stopping when we get to this top region up here, which is given by the intersection with the plane z equals 4. Okay, so that's telling us then our integral goes from z equals 1 minus r squared up to z equals 4. And we already figured out, I guess, that our integrand is k times r. That's our density. And then we need to figure out, okay, so after we've done this blue vertical integration, what's going to be left? Well, then once again, imagine yourself as, being way up high, looking downward at this whole thing. After doing the integral, what do we see? Well, we see this shadow of the unit circle. Let's go green. Cast down here in the XY plane. Man, tragic unit circle. My unit circle's not looking so good. Let's see this. There we go, slightly more accurate. Okay. So then we just have to integrate over the unit circle. So we've got r equals 0 because the center is included to r equals 1, right? So that's let's see, so going back down here, that's going from the center, whoop, out there. And then the last part is we integrate from theta equals 0 to 2 pi, swinging it around. So we go theta equals 0 to theta equals a full circle. Okay, and we've got ourselves a Jacobian and a dz and a dr and a d theta, and we're ready to rock and roll. Now, that would be the good way to set this one up, but you know what I like to do? I like to do things the hard way, just to make sure that you can actually do it. So let's look at this thing again, and we'll look at just like a side cross section. So here's the center axis coming down, and then there's that bit of parabola that's like notched out at the bottom. Okay, so now what if we were going to do dr first? So imagine that you were bound and determined to go r equals this to r equals that, k r squared dr dz d theta. Okay, well, let's see. So now what we're doing is we're saying, okay, so if we start at the axis and go outward, what do we see? And so for the top part here, you start at the center. For the bottom part, however, you start at the parabola. So the first thing you see is that this is not an elementary region to set up this way, and we would have to split it and make two integrals. So for the bottom integral here, we have that this central axis is actually incorporated. This is part of the object. It's inside it. So we start at 0. So we're going to go from r equals 0 up to, and then this outside line right here is r equals 1. And then let's see, so that's going to be now from this height, z equals 1, which you can work out by substituting one equation into the other, up to this one up here, which we already noticed is z equals 4. This bottom, this downward begins at z equals 0. So this one is going to be from z equals 1 to z equals 4. And then theta goes all the way around. So we have that part. But now we're also going to need to take into account this bottom integral right here. So that's the top part, and we need to do the bottom part. And so for this one, we're going from theta equals 0, theta equals 2 pi, from z equals 0 to z equals 1. And then when we go to figure out what the r bounds are, we notice that for this part, the central column here is not part of the region. This is the excavated cavity, the part that got drilled out, right? So this is not in the region. And when we have a line going outward radially from here, the first place that it hits is along this curve, this paraboloidal surface. So that's where it begins. So we want to start from r equals paraboloid, and then we're going to go outward until we get to r equals cylinder. And so that part we already saw. That's r equals 1. And for the paraboloid part, we're going to take our z equals 1 minus r squared and flip it around and solve it the other way, and we see that this is r equals 1 minus z squared. So this is r equals 1 minus z quantity squared. Okay, so that's how you would set it up in the other order if you wanted to do it in the other order.